Hello everybody, my name is Nicolas Rinaudo and I'm here today because I'd like to talk to you about algebraic data types. Because over the course of my career, I have had to design many data structures, and I have come to the conclusion that you can do so in essentially one of two ways. You can either do it with algebraic data types or you can do it wrong. And I have done it wrong quite a bit. So the purpose of this talk is for me to show you all the ways that I have done it wrong so that you don't repeat my mistakes. And the promise is that by the end of the talk, you will understand all the properties that make algebraic data types so important and so useful. And this should have a lasting impact on the way you write code. Now, there is a little bit of a backstory to this talk, because a while ago, I was talking with my wife and complaining about some of the feedback I had gotten on a previous talk, about how my examples were a bit too dull, not very fun, and that, as a result, my talk itself was a little bit boring. But my son was around, and hearing that, he told me not to worry about it, and that for my next talk, he'd pick the example. So, given that my son is 6 years old and half Japanese, today we are doing Gundam. I must admit that I don't actually know much about Gundams, aside from the obvious giant robot that goes pew-pew aspect. I understand that apparently sometimes they can grow wings, and then you have to stop calling them Gundams and start calling them Gundam wings, but I don't know. I don't actually know all that much about them. And you might think that giving an entire talk that focuses on Gundams when you hardly know anything about them might prove to be a little bit of a challenge. Turns out you're absolutely right, but I think I make it work, and I'll let you be the judge of that. So what we're going to do today is we're going to remote control Gundams via an old Super Famicom gamepad controller. And the way that works is that we can send commands to Gundams. And at least initially, Gundams have a very limited vocabulary. The commands we can send are, for example, face north, which will cause the Gundam to turn north, face west, and it will turn west, face south, and it'll turn south, and face east, and it'll turn east. Then you can also ask Gundam to start, which will cause it to start walking in whatever direction it was facing at the time. And you can ask it to stop, which will obviously cause it to stop. And these are all the valid commands that we can send a Gundam. But we can, however, send any number of invalid commands, such as, for example, triple backflip. That doesn't actually make any sense. The Gundam doesn't understand what that means. That's going to cause it to hesitate. And we all know what happens to a Gundam that hesitates, even for 1 second on the field of battle, don't we? That is technically known as an undesirable outcome. And we want to avoid that. And in order to avoid that, I've done a lot of really hard work. I've implemented the Gundam Scala API. So now Gundams are equipped with a virtual machine that can run valid Scala bytecode. And should that Scala bytecode throw an exception or result in an ambiguous or illegal state, then the Gundam is going to blow up. But the key here is what we send the Gundam is bytecode. So we have a tool between our code and the execution that is going to help us avoid bad programs. The compiler. If we can make it so that commands such as this, face of -35, does not compile, then the Gundam will not blow up and live to fight another day. So this is what we'll be trying to do for the rest of the talk. The first thing we'll have to do is to design a type for direction, which, as we saw, was either south, north, east, or west. And when I was learning programming a few years ago, I was taught that the best way of representing these kind of things was to use magic values. Open a namespace, direction, and then stick values in there, north, which we arbitrarily say is an int of value 1, then east, which is 2, south, which is 3, and west, which is 4. Now, that kind of works for a few seconds, but this is going to break down really quickly because well, say, for example, in the Scala Gundam API, I have put a few helpers, such as a label function that, given a direction, returns a pre-printed label for that direction. So that function takes an int, because our directions are ints, pattern matches on it, looks at the value, and maps it to the corresponding label. What do you think happens when I run that label of -35? Well, -35 is a valid integer, label takes an integer, so the compiler is very happy with this. But we get a runtime explosion because we haven't handled the -35 case in our pattern match. So this obviously doesn't work. We need something better. And the next thing I was taught to try was to use a feature that Scala has, which are type aliases. You can in Scala say this, our type direction is equivalent to int, which allows us to rewrite our directions to be of type direction, which is a bit nicer. And it also makes a lot more sense when we go to look at label, because now label takes a direction, not an int. So it's a major step forward, at least for the human reader, because now it's very clear that we don't take any int, we just take a direction. So that's an improvement for us, the reader. As far as the compiler is concerned, though, -35 is a valid int. An int is equivalent to a direction, so this type checks. There is no problem here, except when you try to run it, and we get the same explosion as before. So none of this worked, but we have other tools at our disposal. Specifically, most languages, Scala in particular, support something called an enumeration. In Scala, it goes a little bit like this. You define an object direction and say it's an enumeration. And in there, you would declare values north, east, south, and west. And there we go. We have a direction, we have an enumeration whose only possible values are north, east, south, and west, which allows us to rewrite label. Now, this is a little bit awkward because it doesn't take a direction anymore, but a direction.value, which I think is not very pleasant. It's a bit of a mouthful. But if this is what it takes to save Gundam kind, then let's do that. And now, thanks to this new type, the following code fails to compile, and we have saved our Gundam. At least for the moment. Because unfortunately, enumerations, or at least the way they have been implemented in Scala, suffer from a pretty drastic flaw. For example, imagine a scenario in which you have to debug some code. I don't know how you debug code. A lot of people use fancy debuggers. I comment stuff out and use print line statement all over the place. And here, I thought there was something dodgy with the way I handled direction.west, so I commented it out, forgot to uncomment it, compiled everything, and now what do you think happens when I run that? Well, direction.west is a perfectly valid value of type direction.value, and label takes any direction.value, so this compiles, but blows up at runtime because we're not dealing with the west scenario. And this is known as a pattern match exhaustivity checking problem. The compiler should know that all the possible values are north, east, south, and west. Knowing all the possible values, it should know that we have failed to handle one and tell us off, fail to compile because we haven't handled everything we needed to. But Scala enumeration, for whatever weird reason, disabled that behavior. So not good, still not the tool we were looking for. But since the standard library implementation doesn't do what we want, we're going to do what any good developer is going to do. We're going to reinvent the wheel. We are going to write our own enumeration. So we do so by declaring a trait direction that has the possible values, the following possible values: north, which is direction, east, south, and west. And now we have a new type, direction, that only has these four values, north, east, south, and west. And we can try to recompile label, and that unfortunately still compiles and still blows up at runtime. Now, the reason this happened is the compiler does know that the only possible values it knows of are north, south, east, and west. But Scala is an open word thing. There might be other dependencies on the class path. There might be other jar files. There might be some other code that the compiler doesn't have access to right now that extends direction. So the compiler knows at least of 4 values, but it doesn't know that these are all the possible values we can ever encounter. And unfortunately, the Scala compiler, at least in Scala 2, as soon as it realizes it cannot prove exhaustivity, doesn't even bother to check for it, which is why we're getting a runtime explosion here. Fortunately, there's a workaround, because if we flag our trait as sealed, that is telling the compiler there will never be another direct subtype of direction. They will all be present in that compilation unit. Nobody else is ever allowed to subtype it. So with that, if we try to compile this bit of code, the compiler knows exactly all the possible values that we can encounter and will refuse to compile our pattern match because it's incomplete. What have we learned so far? Well, we have learned that enumerations make nonsensical values impossible to represent because we cannot execute face of -35 or anything like that again. That guarantees that our code handles all necessary cases, no weird loophole in your code through which production data can sneak in and blow your Gundam up, because your compiler will tell you off as soon as you forget to handle a case. That is only true if you don't use Scala enumeration, though. Just don't use them, they're rubbish. Right. We have a model for direction, we have represented these, and now we need to do the commands that we have defined. Now, if you remember, we have face, which takes a direction, start and stop, which don't take a direction. So a naive way of representing our command class would be to use a record, which in Scala we do as a case class. That is composed of an order, string, which is either face or start or stop, and a direction, which has to be optional because face takes a direction, but start and stop do not. This looks like it might work up until the point where you try to run that. Triple backflip is a completely valid string, so the compiler is going to accept it, and we're going to get a runtime explosion. But fortunately, we know exactly how to deal with that situation, don't we? Because we've just seen that with directions. We have a known set of value, face, start, and stop. So instead of using a string, we can use an enumeration order, which is a sealed trait, with the values face, start, and stop, which allows us to refactor command to not take an order as a string, but an order as an order. And this works a lot better because now triple backflip will not compile because that's not a valid order. Unfortunately, though, this does compile, but it doesn't make any sense. Start south is not a valid command for the Gundam, and that is going to cause a runtime explosion again because it's an ambiguous statement. It's an illegal statement that does not exist in our vocabulary. And we want to avoid representing that. And the problem, of course, is that the way we have designed our command class, we can have a direction specified for start and stop, which doesn't make sense, and we can forget a direction for face, which doesn't make sense either. So since only face takes a direction, we could rework order to reflect that information. Face takes direction, but none of the others. In this way, we have exactly what we wanted, don't we? Because face takes direction, nobody else does. It is so much exactly what we wanted that what we have here is not order anymore. It's actually the type command that we wanted to write all along. And now, with this new command, it is impossible to write start south. This will be rejected at compile time. But we could, of course, write command.start or command.face south. Both of these work. And cause the Gundam to move. What have we learned so far? We've learned that enumerations are absolutely everywhere. They are the very first tool we reached for when we faced a problem here, and they mostly solved our problem. But they're not quite enough. We did have to tweak order a little bit in something that is not an enumeration anymore. But something very much like an enumeration might, however, be enough for what we want to do. And in order to explore that something like an enumeration thing, I want us to try and compose commands. Because at the moment, this is what we can execute, a single command. It's a little bit boring. What I want to do is to have multiple commands treated as a single command, and that the Gundam would accept, and then go through every one step by step. And of course, the answer to the question was in the question, I said that the composition of commands should be a command. So there's only really one way we can go about that, isn't there? We need to go back to our command class and modify it to have a new chain command. And a chain command is a first command and then a second one, so that the Gundam is going to first run the first one and then the second one. It actually looks like we're done. We can compose commands now, up until the point where you actually have to write a compound command, because it looks something like this. If you squint, you can sort of make it out. This is telling the Gundam to face east, then start, then stop. Then to face west, then start, then stop. But this is not very pleasant to read, and I had to write that, and it was not pleasant. I do not want to do it again, and I do not want to show you another slide that looks like that. So we're going to do what every good Scala developer does whenever faced with this kind of situation, or even given half a chance. We're going to write a DSL. Now, the mechanics of the DSLs are not at all relevant to this talk, but the way this works, roughly, is if we have a first command, cmd1, we can squiggly arrow it into a second command, and that's going to return the composition of both commands. Now, standard practice when you write a DSL is also to provide aliases for the terms in your vocabulary. So we're going to do that. Start, stop, and face, as well as for directions, north, east, south, and west. And now we can write a much more terse, a much simpler command, move, which, given a direction, is going to face in that direction, then start, then stop. And that allows us to rewrite that entire messy page we saw before to just this, where it's going to be accepted by the compiler and the Gundam is going to execute it. Start east, face east, start, stop. Then face west, start, stop. And what have we learned? Well, we have learned that we have completed our data type by using records, chain and face are records, are case classes, enumerated types like command and direction. But in order for that to work, we also had to make command recursive, because command is expressed in terms of itself, since chain is a command that contains a command. So command is a recursive data type. And these three characteristics are all I needed to be able to finally give you a proper definition of what an algebraic data type is. An algebraic data type, such as command, we've seen that command is a face, or a start, or a stop, or a chain. And that is very precisely known as a sum type. A sum type is a discriminated union of values, and it can be thought of as an OR on types. Now, there might be something that bothers you a little bit about that definition. And if you're not sure what it is, I'll tell you, it's this word, discriminated. I haven't earned the right to use it yet, have I? You don't know what it means. I haven't shown you or explained anything that seemed related to that. But the reason for that is, in Scala, you cannot declare a union type that is not discriminated in some way. So it's really very hard to show you something that cannot be expressed in the language. So in order to show you what discriminated means, what I'm going to have to do is to write a little bit of C code. So if we have anybody here who used to do C, or God forbid still does C, you might want to look away for the next couple of minutes, because I do not want to trigger your PTSD. But for the rest of you, this is how we used to have to do union types. Int or string is either an int or a string. That looks pretty straightforward. That looks very normal, up until the point where you actually try to use it. If you want to print one, you can't really, can you? Because while you know that you have an int or a string, you don't know which one you have. So there's really nothing you can do with that data. And in order for us to be able to actually do anything with it, what we used to have to do was to create an enumeration, which we often call type tag, which has two possible values, int tag and string tag. So we use that to describe the values we have in our union type. By doing so, our int or string has a new field called discriminator, which we'd use to know which is which. And of course, this is not a union anymore because it's the association of a discriminator and a value, so it's become a struct. And we need this to be a union again, so that now we have everything we needed. We have an int or a string, and some sort of value that tells us which is which. And with all that information, we can finally write print union. First, a little bit of cleanup. Int or string is not a union, but a struct now. But then the rest is straightforward. If our discriminator tells us that we're working with an int, then we treat the value as an int. Otherwise, we treat it as a string. And all that work, and that is a lot of work, isn't it? And it's a lot of work that we have to do every single time, or at least had to do every single time. It's also very error-prone, because it's really very easy to somehow get mixed up and have the discriminator say that the data is an int when it's actually a string, or vice versa. And in C, that's kind of fatal, because you never know what happens when you have the wrong type. Anything could happen, it's C. And people decided, very smart people decided, well, all this work, it looks like it could be automated. It's always the same work, all the time. So I could get the compiler to do that for us. I could somehow have the compiler generate automatically behind the scene a discriminating value that allows us to know which value we're dealing with. And that is a discriminated union type or a sum type. This is exactly where we are. And in Scala, the discriminator that we use is the run type class of the value that we're working with. It can be something else. I believe that in OCaml it's a byte. Not entirely sure. Haskell is probably an int. I'm not entirely sure. But some types will have under the hood some sort of discriminating value and some ways of working with that, which happens to be pattern matching. Right. So we know that algebraic data types are sum types with some more information. Command is a chain, but chain is a composition of a command and another command, the first command and the second command, isn't it? And that is known, the first command, and the second command. And that is known as a product type. A product type is an aggregation of values, and it can be thought of as an and-on types. So we now have a better definition of algebraic data types. We know that there are some types of product types. But we're not quite done, because there's something specific about command. It is defined in terms of command. Command is a recursive type, so algebraic data types can be recursive, which gives us our final definition. An algebraic data type is a potentially recursive sum type of product types. And this is the main point that I wanted to make. What have we learned? We've learned that algebraic data types are sum types of product types, and they are potentially recursive. And that's really all there is to it. We could, however, explore this notion a little bit further, because this is something I have to admit, I have been lying to you just a little bit by telling you that we could compose any command together. But that's not actually true. Some commands are unsafe to compose together. For example, start followed by start. When you run the first start, everything is fine. The Gundam was stopped, it will start. But when you get the second one, it's confusing, isn't it? He's already started. What do you expect it to do? And we know what happens when a Gundam gets confused. We get a runtime explosion. Similarly, if we send two stop commands, first stop command is fine, but the second one, the Gundam is already stopped. We get a runtime explosion. And let's not even talk about starting and then changing direction mid-stride. That's never going to end well. So what we want to do here is to prevent these things. We want to be able to keep track of the Gundam state so that we make the composition of commands that don't make sense a runtime type exception, a compile error, sorry. And again, the answer to the question is in the question itself. We want to keep track of the state of the Gundam. And we also want to do that at the type level because we want the compiler to be able to do that. And this means that we need to have some sort of type that describes the state of the Gundam, which we can do fairly easily this way. Idle means that the Gundam is not moving, and moving means that the Gundam, well, is not idle. And if you look at these types, they're final and abstract. Abstract meaning that you need a subtype to be able to instantiate it, and final meaning you can't have a subtype. So basically, these two types mean there's never going to be a value of type moving or idle. They're just types, just here for the compiler. And armed with these two types, we can update command now to have two type parameters, before and after. Before is going to be the state the Gundam must be in before it can run the command. And after is the state the Gundam is going to be in after it has executed the command. Which allows us to rewrite face. Now, face, we know that we have to be idle, we have to be in a stopped position before we can change direction, and we'll still be in a stopped position after. So it's a command of idle to idle. Start goes from idle to moving, so we have a command of idle to moving, and stop goes from moving to idle, so we have a command of moving to idle. Now we get to chain, which is the clever part, the part that is a little bit complicated, but that handles everything. We have a first command, which can be from any A to any B. We don't need to know anything about them. But the second command, however, cannot be from any type to any type. It must start from a B, because we need the Gundam to be in a state that is compatible with the next command. So we need the first command and the second command to commute. And the composition is going to take us from A to B and from B to C, so that's going to be a command from A to C, which we have now declared three type parameters, and we need to actually declare them to be able to use them. And that is essentially everything we need. We do need a quick update of the DSL. The first command goes from any A to any B, and I need to be able to declare these types to be able to use them. And our second command must go from B specifically to any C, and I need to declare that type parameter to be able to use it. And the composition is going to be a command from A to C. And now that we have done all that, start followed by start has become a compile error. It's not possible to do it anymore. Stop followed by stop has become a compile error again. This makes sense because stop puts you in an idle position and stop must start from a moving position. So you get a type mismatch. You wanted moving, but you get idle. And finally, start followed by face fails for exactly the same reason. Now, you might think, grand, we've made everything impossible. But we haven't. Whenever the types match, we can execute the code. So this, for example, type checks completely, and we get face east, start, and stop, and everything works exactly the way it should. We get a little bit more than just that, though. This is great already, because now we cannot represent illegal state transitions. Not only can we not represent illegal state, but we can't represent illegal state transitions. This is really nice already. We don't have to deal with impossible scenarios. But we have also made pattern matching slightly more powerful. Look at this function, moving label, which is basically the same as the label we had before, except it works for a command whose first type parameter is moving. Now, in this pattern match, I only deal with command.stop, which we know matches because moving, must start from moving and goes to idle. And I also have to deal with chain because, well, there are some chain commands that start from moving, typically stop followed by start. And the compiler will accept that. But then when I try to run command.start, of course, it'll be rejected because start is a command from idle to moving. So it doesn't type check, and the compiler will reject it. So it's not possible to call moving label with a bad parameter. But it goes further than that, because if I do what I did the other time, debug, uncomment some code, and forget to uncomment it, the compiler is going to complain about it, because it knows that command.chain, it cannot prove that command.chain is never going to have a first type parameter of moving. So since it cannot prove it, it demands that you handle the case because it is a possible scenario. And if I were to fix that and re-put the code for chain, and in a fit of madness add the handling for start, then the compiler is going to tell me off. Because start is not a valid command of moving. So the compiler will prevent us from writing it, which is really nice, isn't it? Because we've already seen that the compiler demanded that we do all the necessary work. We handled all the possible cases. But here, what it is doing is telling us to not do any unnecessary work. It's going to flag the code that we don't need, that's never going to be called, and ask us to delete it. Which is pretty neat, because I'm a lazy person, and the work that I don't have to do is the best kind of work. And the compiler finds that for me. So something else we can do, less often useful, but really very cool. Look at that pattern match here. Specifically at t. What is that? It looks like a variable, right? But it's a type. We have a type in that variable. And not only do we have a type in that variable, but the compiler knows exactly which type. It knows that t must be the type moving because of the type of moving label. Now, to be completely honest, I've never actually used that in real life, but I do find it really very cool that it works. And what have we learned? We've learned that we have used type constraints on our sumtypes members to make illegal state transitions impossible to represent. Because now we can't compose start and start, for example. We also have used it to guarantee that our code handles all necessary cases, but only necessary cases, which are very good guarantees to have. Because we have to do all the work, but not more than that. And of course, one last thing that we've done here is that we have put all the groundwork we needed for me to be able to define what a generalized algebraic data type is. Now, it sounds like a scary word, but we're going to get through it. It's not that complicated. We've seen that command is a sum type. It's a sealed trait with possible values, face, start, and stop. So we know that a generalized algebraic data type is a sum type with some more information. What else have we done? We've seen that we had type parameters before and after, and that these type parameters were used to encode some information about the branches of our sum types. The for tells us what state the Gundam must be in before the command can be executed, and after tells us the state the Gundam will be after it has executed the command. That notion is called a witness type. A witness type describes properties of a sum type's branches at the type level. And finally, so a GADT, is a sum type with one or more witness types. We know that we have two here, so we can have more than one. And finally, if you look at moving label, the way this actually works is the compiler knows that the first type parameter of command must be equal to moving. And in the case of chain, well, the compiler cannot find a proof that the first type parameter of chain is not going to be equal to moving. In fact, it can, because a compound command of stopped followed by start will have the first type parameter of moving. So not being able to prove that this is an impossible scenario, the compiler is going to demand that you do it. And here, the compiler is going to know that moving is not equal to the first type parameter of start, because that is idle. So by being able to compare type parameters and make sure they are equal or not, the compiler refines the pattern match and forces you to deal with all the necessary cases, but only the necessary cases. And that is known as type equality. It is information available to the compiler about each witness type that allows it to refine pattern matches. And that is what a GADT is. A generalized algebraic data type is a sum type with one or more witness types, each equipped with a type equality. Now, this definition is a little bit hard to see when you're doing Scala. Because look at this type. You're probably already familiar with it, option. Most of us are likely to have used it at some point. Well, it is a sum type, isn't it? It's a sealed trait with two branches, sum and none. And if you look at these two things, sum and none, well, they're types, right? So information available at the type level. And not only are there types, there are types that describe a critical property of the branches of our sum type. Sum describes a non-empty option, and none describes the empty option. Those are exactly witness types. And if you look at saveget is a function that, given a non-empty option, will return whatever was stored inside of it. Well, by comparing the value of the witness type, we know that sum is equal to sum, so we have to deal with the sum case. But sum is never equal to none, so we must not deal with the none case. And that is exactly type equality. So that's one of the reasons why generalized algebraic data types can be a little hard to pinpoint in Scala, because it is not possible to define a sum type that doesn't happen to also be a generalized algebraic data type. And it's really very hard to see. It's kind of like seeing the forest for the tree. We have the more powerful version, so why would we need the smaller version, the less powerful version? What have we learned? We've learned that generalized algebraic data types are sum types with interesting properties for pattern matching. And we've also learned that Scala is really bad at helping us see that. But if Scala is so bad at helping us see that, then how about some Haskell? Because it's a lot clearer in Haskell. Take option in Haskell. Option is either a sum or a none. But a very important piece of information here is that sum and none are functions. They're not types. Sum is a function that goes from A to option of A. There is no representation at the type level of whether an option is empty or not, which makes it impossible for us to write safeGADT, because we cannot encode the notion that an option is non-empty at the type level. For that, we need witness types. The code gets a little bit messy, but still very straightforward. Option now takes a new type parameter, phantom, which can be one of empty or non-empty. And armed with that, we create some smart data constructors, sum, which given an A will return a non-empty option of A, and none, which returns an empty option of A. And when we export all of the things we've declared from our module, we conveniently forget the regular data constructors and only export the smart ones, which means that anybody outside of our module will, by construction, be unable to create a non-empty none or an empty sum. But while we know that, or at least we're convinced of that, the compiler isn't. We can write safeGADT and demand a non-empty option. In the sum case, it's trivial. We know exactly what to do. But the none case is still required because the compiler is not convinced that it is impossible to have a non-empty option, to have a non-empty none, sorry. And the reason for that is we haven't equipped the compiler with the tools it needed to reason about the types. We need some form of type equality, which in Haskell we do by making a data type a generalized algebraic data type. And option looks the same as before, but now the data constructors already contain all the type information that we have. Sum takes an A and returns a non-empty option. None takes nothing and returns an empty option. And armed with all that, now that we have generalized algebraic data types, safeGADT works exactly like we wanted, because the compiler is now convinced that it is impossible to have a non-empty none, and is fine with us not handling that scenario. We can also do something which is really, really kind of cool, although I'm not sure how useful it is, but it really, really is nice. Take OPT here. OPT is of type option of phantom of A. The phantom can be anything. It can be empty or non-empty. We don't know. However, in the sum case, we get to call safeGADT on OPT. But if you remember, the signature of safeGADT was it takes a non-empty option, which is a little bit weird, isn't it? Because OPT does not contain the information whether it's empty or not. Except, as far as the Haskell compiler is concerned, it does in a sum branch. In the sum branch, and just in that sum branch, we know that OPT is of type option of non-empty. So the compiler, thanks to type equality, is capable of refining the type of a value within the context of a given pattern match branch, which I find absolutely incredibly cool. What have we learned here? We have learned that Haskell makes generalized algebraic data types very clear. We have some types, option, witness types, the phantom parameter, empty or non-empty, and type equality, which is what we get for GADTs. And if I had done my entire talk in Haskell, it would have been done about 40 minutes ago, because Haskell makes it far easier to see all of these things. Now, in closing, if you only remember a single slide from this talk, let it be this one, because that's the slide in which I point out that I have delivered on my promise. I told you that I would show you, and you would understand, the properties that make algebraic data types special and important and useful. And I have, because they make your data structures simpler and safer. Simpler because, thanks to algebraic data types, you have made impossible states, illegal states, impossible to represent. And it's a very straightforward argument to say that code that doesn't handle impossible scenarios is simpler than code that does handle impossible scenarios. And it's also safer because algebraic data types give your compiler the tools it needs to be able to just lock down your code and make sure that you have no holes in your data handling that will allow bad data, bad production data, to sneak into your program and blow your Gundam up at runtime. Generalized algebraic data types have the same properties, just only a little bit more so. But, and very importantly, thinking about data structures that way, as algebraic data types, will have a lasting impact on the way you write code. And it will do so even if your language of choice happens to not be Scala. Sorry, happens to not support algebraic data types. It can in fact be argued, and it has been argued, that Scala, or at least Scala 2, doesn't properly support algebraic data types, because some types are just a little bit dodgy in Scala 2, and generalized algebraic data types are kind of a mess in Scala 2. There's a lot of bug in type resolution, which as soon as you try to do something complicated, it will stop working. Scala 3 mostly solves this problem, but I understand that there's still a few holes in generalized algebraic data types handling in something called open generalized algebraic data types. To be completely fair with you, I understood the argument a few weeks ago when I read the paper. Don't remember it now, and I don't even remember what an open generalized algebraic data type is. So, if anybody in the audience knows what that is and knows the argument, it's not at all unlikely given the crowd that we have, then please feel absolutely free to explain that to us in the questions. I can't hear you. I cannot hear you.
Thank you. Sorry about that. We do have a couple of questions, and I'd like to at least ask one up on the stage. First question, are there any performance concerns using ADTs?
Not that really comes to my mind. It's not even a question that I have considered. So I have never encountered any, but that doesn't mean that there are any because I haven't really looked for one. So, sorry, it's a bit of a disappointing answer. I don't think so.
Okay, our next question is, in the chain, would it be possible to hide intermediate state B to the outside world?
It kind of is, isn't it? Because when you have a value of type chain, the only type parameters that you have are A and C. So provided you have a chain, you know A, you know C, but you do not know B. So that's one possible interpretation of that question. And if my interpretation of the question was correct, then this should answer it. If your question was, can we hide the states altogether, because it's a bit of a pain to have to carry over this A and this B and this C all over the place, then we could definitely make the type parameters abstract type members of command. But I try to avoid doing that because I very often, well not very often, but sometimes encounter some resolution issues when I have abstract type members, and I find them a bit more cumbersome to use than type parameters. So I guess we could, but I prefer not to, and I don't see a clear benefit to doing it.
Well, thank you.
You're quite welcome.
There is a couple more questions in the Hopin Q&A area in the Stage tab. If you would be so kind to answer those in text, we would really appreciate it.
No worries at all. I'll be heading there right away.
Great. Thank you
Thank
again.
you very much.
Yep. Thank you for being.